Antarctica looks silent, but beneath kilometers of ice, something is burning. Chinese scientists have uncovered a vast chain of hidden volcanic fires trapped under ice.
Right now, at the absolute top and bottom of our world, two frozen systems are acting up in ways nobody saw coming. Scientists who spent decades watching these remote areas had to stop and recheck their instruments recently because the new satellite numbers simply did not line up with old predictions. The far north and the far south are breaking down for completely different reasons, and nobody saw it coming. The illusion of stability. Back in the late 70s, when satellites first started tracking the Arctic Ocean, scientists saw a steady drop in sea ice year after year. That made total sense because overall global temperatures were rising. But right around 2005, that predictable downward trend suddenly stopped. Every single year between October and March, the sun sets over the North Pole, and pitch-black winter cold freezes the ocean surface into a large sheet of ice. Between 2005 and 2024, that winter ice cap stayed low compared to the 1980s, but it completely stopped shrinking any further. If you plotted those numbers on a graph, the line would look flat. So researchers started looking at that flat line and figured Arctic winter ice had hit a stable holding pattern. Some experts even published papers arguing that winter sea ice loss had officially leveled off. That comforting idea held strong for almost 20 full years. Folks started to relax a bit, thinking maybe the worst warnings were a little bit off. But the whole time, heat was secretly gathering under the surface. The flat line was never a real sign that things were fixed. It was just a brief break sitting right on top of a much bigger drop, waiting for the right moment to snap. So what happens when 20 years of hidden pressure finally finds an outlet? The answer came out of nowhere, and it totally shattered what everyone thought they knew about the North. The 2025 to 2026 Arctic crash. Between the winter of 2024 and the winter of 2025, Arctic sea ice took a sudden hit during its main growth season. In just 12 months, the frozen ocean cover fell by roughly 6%. That single number might sound kind of small when you hear it out loud, but 6% of an ice cap means a chunk of frozen water roughly twice the size of Texas just vanished. It was the biggest year-to-year drop during the cold months ever recorded since satellite eyes started watching from space back in 1978. And the real kicker was the timing. This huge loss happened right at the moment in the calendar when the North Pole is supposed to be at its strongest, sitting under months of freezing polar darkness. Instead of building up a thick, solid shield, the ice was struggling at the bottom of the barrel levels nobody had seen in almost 50 years of careful measurement. Researchers at the University of Southampton and the National Oceanography Center in the United Kingdom immediately ran complex computer simulations to see if a drop that steep was even physically possible under current global conditions. They looked through decades of climate data, trying to find anything that matched what just happened. They did find a few rare matches, but those models revealed something else that really bothered the team. In 2026, the peak winter cover actually bounced back just a little bit, but the simulations showed that a tiny bounce like that is not a real recovery. When a drop is that violent, the ice almost never snaps back to its old self. Instead, it settles into a new, broken baseline and wobbles around at much lower levels. NASA and the National Snow and Ice Data Center confirmed the bad news using their own orbital sensors. On March 15, 2026, the Arctic peak hit 14.29 million square kilometers. That puts it in a statistical tie with the 2025 record low of 14.31 million square kilometers. For two back-to-back years, the top of our world logged the absolute lowest winter caps ever documented. Senior scientist Jennifer Francis compared this trend to a scary warning sign during a regular medical checkup. If your vitals keep showing bad numbers test after test, you do not just sit back and wait for a total heart attack before you start taking action. Well, climate experts are saying the exact same thing about our northern ocean right now. The polar thermostat in reverse. When you look at the top of the globe during the coldest months of the year, that thick blanket of white is not there only to give polar bears a place to walk around. It acts like a giant insulating lid sitting over a warm room. The ocean water trapped underneath that frozen crust stays right around 28 degrees Fahrenheit, which is pretty chilly for a swim, but it is actually much warmer than the air right above it. Out in the open polar night, the atmosphere drops to 30, 40, or even 50 degrees below zero. When that solid lid stays thick and tight, it locks all that ocean heat inside the water where it belongs, keeping the freezing sky and the liquid sea totally separated. But when that lid starts thinning out or cracking open, the whole system goes completely haywire. Heat starts leaking straight out of the water and shooting right up into the cold sky all winter long. That extra energy does not just sit there over the remote North Pole either. It messes with air pressure and pushes the high-altitude jet stream out of whack. Scientists have been linking these gaps in the northern lid to those sudden cold snaps and crazy winter storms that hit places like the American Midwest or Northern Europe. So losing that frozen layer up top is not just some distant regional statistic. It is a massive lever that directly pulls on the daily weather systems we all live under every day. And that brings us to the main engine behind this entire breakdown, something scientists call the albedo effect. The basic concept is actually quite simple. Fresh snow and ice act like a gigantic mirror, bouncing up to 90% of the sun's rays straight back out into deep space. Dark surfaces, like open ocean water, do the exact opposite. They soak up almost 90% of that solar energy, trapping the warmth like a dark shirt on a hot summer day. So when a patch of bright white cover disappears and leaves dark water behind, that spot stops reflecting light and starts soaking up heat instead. That extra heat warms the water underneath, which makes it even harder for new frozen cover to form when winter comes back around. That missing layer leaves even more dark ocean exposed to the sun the following year, which traps even more heat, and the whole cycle spins faster and faster. It is literally our planet's natural cooling system working completely in reverse. This unstoppable loop is the main reason why the far north is warming close to 4 times faster than the rest of the globe right now. Every single mile of white cover that vanishes is not just a sad symptom of a warmer world. It turns into an active driver that makes the next season even hotter. Now, for a long time, people thought this kind of wild chain reaction was only happening up north, while the bottom of the globe stayed totally safe and sound. But while everyone was staring at the Arctic, something completely unexpected was gathering strength at the South Pole. Antarctica's decades of immunity, 1979 to 2015. Up north, the Arctic is basically a deep ocean surrounded by big chunks of land. Down south, Antarctica is the exact opposite. It is a large, frozen continent entirely surrounded by a stormy ocean. That single geographic difference changes how warmth interacts with the polar environment. Back in 1979, when those early satellites began taking daily measurements of the Southern Ocean, scientists watched the northern ice drop year after year. But down around Antarctica, the numbers refused to follow that downward line. Instead of shrinking, the floating frozen belt around the southern continent held totally steady. In fact, during plenty of winters, it was actually growing larger. Year after year, while atmospheric temperatures rose everywhere else, the far south looked like it had an extra layer of protection. For a long time, experts had a solid explanation for why the South Pole seemed totally immune to the changes happening everywhere else. Strong winds known as the westerly belt were constantly whipping around the continent like a spinning barrier, keeping warmer air trapped far away to the north. At the same time, fresh meltwater poured off the continental glaciers into the sea, forming a top layer of lighter and colder water that froze over easily every single winter. That surface cap blocked warmer ocean currents down below from reaching up to touch the frozen cover. So for nearly 4 decades, Antarctica looked like the one place on Earth that could simply ignore global warming trends. Whenever skeptics tried to claim that polar ice loss was exaggerated, they almost always pointed straight to the stable southern numbers as their favorite proof. The continent seemed permanently locked in ice, completely insulated from the rapid changes tearing up the far north. Then, right around 2015, that long-standing stability started showing subtle cracks. The long stretch of steady growth came to a grinding halt, and the protective ocean layers started changing in ways nobody had ever documented before. The decades of floating armor were about to come to a sudden, violent end, leaving scientists scrambling to figure out how the most stable ice system on the planet could transform into a total runaway wreck overnight. The triple whammy. The southern continent's legendary protective armor did not just wear down over time. It basically fell apart right at the end of 2015, kicking off a chaotic downward slide that caught everyone off guard. Satellite sensors caught a steep drop in late 2016, which marked the first major record low of the modern era. If anyone hoped that sudden dive was just a weird one-off fluke, the following years quickly set the record straight. The ice struggled season after season, hitting another low point in 2022 before dropping off a total cliff in 2023. During that 2023 crash, the hole of missing ocean cover grew so absurdly big that it was larger than the entire landmass of Greenland, just gone. Researchers at the University of Southampton dug into the data to figure out what could possibly trigger a collapse that fast. What they found was a brutal combination of three environmental forces slamming the Southern Ocean at the exact same time. The team dubbed this multi-front attack a triple whammy, which is a fancy way of saying three totally separate problems lined up to trap the region in a nasty, self-reinforcing downward loop. The first punch landed right at the ocean surface, where rising thermal energy began chewing away at the cold freshwater buffer. For decades, a thin layer of chilly and fresh meltwater floated right on top of the sea like a protective blanket, giving new ice a reliable surface to freeze over every single winter. Once that cold buffer thinned out, warmer ocean water underneath sloshed straight up to the surface, making it nearly impossible for thick ice caps to form during the dark months. The second punch came straight out of the sky and was driven by major changes in the southern annular mode. This atmospheric pattern locked into a strongly positive phase, which completely rearranged air pressure across the Southern Ocean. Low pressure dropped right over the water near the continent, while higher pressure piled up further north. That pressure gap was like a giant pump that cranked up the westerly winds and blasted warm air directly into the Antarctic peninsula. During the third hit, changes in global ocean currents began pulling up a layer known as warm, deep water, bringing hidden thermal energy straight to the surface. Instead of just dealing with warmer air up top, the ice was getting cooked from below by deep currents that had stayed safely tucked away for generations. Any single one of these hits would have been a headache, but all three landing at once completely broke the system. Antarctica went from a self-cooling fortress into a volatile loop that keeps speeding up its own decay. If you look at a satellite map today, the place looks totally divided. Along the Atlantic sector and near the peninsula, the ice loss looks like a runaway train. But over near the Ross Sea, things look surprisingly normal, thanks to strong southerly winds blowing off a persistent atmospheric feature called the Amundsen Sea Low. That exact same air feature pushes warm northerly air straight into the Bellingshausen Sea right next door, which gives us the wild sight of one coastline freezing while the bay next to it melts into open water. The 2024 East Antarctic Winter Heatwave. Right in the middle of the Antarctic winter in July 2024, when the sun drops completely below the horizon and leaves the continent in pitch-black cold, something happened that made meteorologists double-check their computer screens. East Antarctica, a region that is usually one of the coldest places in the solar system, experienced an atmospheric shocker that completely shattered historical records. Temperatures across a large stretch of the inland plateau spiked by up to 28 degrees Celsius above the normal seasonal average. And that extreme thermal surge stuck around for over 2 full weeks straight. If you need to put a 28 degrees Celsius jump into perspective, you have to translate those numbers into a location where people actually live. Imagine standing in London or Chicago in the middle of January, pulling on a heavy parka while expecting a freezing morning, and stepping outside into 95-degree Fahrenheit summer heat instead. That is the exact mathematical equivalent of what hit East Antarctica in the dark of winter. The absolute numbers were still cold by human standards, but for an environment built on uninterrupted sub-zero freezing, a surge like that was a total freak event. Researchers who analyzed the data afterward discovered that this was not just a brief stroke of odd weather. It was driven by a perfect storm of atmospheric failures working together. First, the polar vortex, which is the tight ring of fast-moving air that usually acts like a giant atmospheric fence, keeping cold polar air locked inside the continent, suddenly weakened and wobbled out of place. That structural failure allowed a huge atmospheric river, basically a giant highway of warm air flowing straight from the tropics, to punch directly through the fence and push deep into the continental interior. Making matters worse, the offshore ocean cover that normally acts as a physical barrier against warm maritime air was sitting at record low levels. Without that icy buffer along the coast to cool down incoming air masses, the tropical heat surge rolled inland without losing any of its power. Supercomputer simulations run by climate modeling teams confirmed that human-driven atmospheric changes played a direct role in making the heat wave significantly hotter and lasting far longer than anything that could happen naturally. What really unsettled the scientists studying the event was the realization that this was not a one-time anomaly that we can just check off the calendar and forget about. The published research clearly framed the 2024 heat wave as a preview of what is coming down the road as global temperatures keep climbing. When the air above the ice sheet warms up that fast, even in winter, it alters the atmospheric dynamics of the entire southern hemisphere. The Hector case study. When floating sea ice melts away into the ocean, it does not directly raise global sea levels because that frozen water was already floating and displacing its own weight, much like an ice cube melting in a glass of water. The real danger to coastal cities worldwide comes from land-based ice, the gigantic glaciers and inland ice sheets that rest on solid bedrock. But sea ice acts as a protective bumper that holds back those inland glaciers. When the floating bumper disappears, the land ice behind it starts sliding straight into the sea. And nothing illustrates that process better than the recent breakdown of Hector Glacier. Sitting along the Antarctic peninsula, Hector recently earned the alarming title of the fastest retreating glacier ever documented in the modern satellite record. Over a brief period measured in months rather than decades, the glacier's grounding line, which is the exact spot where the ice stops resting on solid rock and begins to float on the ocean, pulled back by roughly 8 kilometers. Even crazier, nearly half of that total collapse happened during an extraordinarily short window of time. Scientists who are currently studying the event discovered that the main reason for this rapid collapse came down to the shape of the land hiding underneath the ice itself. Many traditional glaciers rest on bedrock that naturally slopes upward toward the coast, which creates an uphill ramp that acts like a set of brakes to slow down a retreating glacier as it moves backward. Hector, however, sits on a completely flat and slippery stretch of seabed that lies far below sea level. Once warm ocean water seeped beneath Hector and forced the ice to lose its grip on that flat bedrock, there was zero physical friction left to stop the collapse. Without a natural rock barrier to hold it in place, large slabs of grounded ice broke away in quick succession, shattering apart far faster than any classic computer model had ever predicted. This structural breakdown was a wake-up call for glaciologists because Hector is not an isolated case. Large sections of West Antarctica, including huge systems like Thwaites and Pine Island Glacier, sit on similar below sea level bedrock with flat or backward-sloping ground beneath them. If those much larger glaciers experience the same kind of rapid grounding line retreat, they hold enough frozen water to raise global sea levels by several feet. Deconstructing the debate. Whenever polar data makes headlines, it does not take long for debate to break out. People naturally ask, Whether these sharp drops are truly unprecedented or if we are simply watching natural climate cycles play out over a long timeline. It is a fair question, especially since individual studies and occasional cold years get pulled out of context to claim that the overall warming trend has stopped. One of the main points brought up in these debates is that older climate forecasts missed their exact dates. Decades ago, some early computer models predicted that polar summer ice would completely disappear long before now. When those specific calendar dates came and went while the ice was still there, critics used those missed timelines to argue that the whole underlying science was faulty. But there is a huge difference between a specific timing estimate, missing its target date, and a multi-decade physical trend measured continuously by space sensors. Another common argument points to short-term bounces in the data. For instance, after the massive Arctic crash in 2025, winter cover in 2026 registered a tiny uptick. Skeptics pointed to that small increase as proof that the system was healing itself. But a single year of partial recovery sitting inside a 5-decade downward slide is not a trend reversal. It is the exact same pattern you see in the stock market during a long crash, where bad years are occasionally followed by temporary bounces before the market drops down to a new lower level. There is also a popular misconception that the North and South poles are somehow directly linked, as if a collapse up top triggers an instant reaction down below. In reality, the Arctic and Antarctic are separated by an entire planet, totally different ocean basins, and completely opposite geography. What connects them is simply a global climate system accumulating excess thermal energy, which expresses itself through whatever local vulnerability exists at each pole. The confidence behind current polar science does not rest on computer guesses or alarmist headlines. It relies on nearly 50 years of continuous, cross-verified observations from independent space agencies around the world. Satellites operated by NASA, the National Snow and Ice Data Center, and Japanese space agencies use advanced microwave radiometers. These specialized sensors do not rely on visible light, meaning they can map ice thickness and extent straight through total winter darkness and thick cloud cover with absolute precision. When multiple independent research groups using different satellites and processing methods land on the exact same numbers year after year, the baseline trend becomes impossible to ignore. A single cold winter does not undo a multi-decade slide, and short-term wobbles do not erase the long-term physics. But as both poles continue to trend downward, scientists are closely tracking one specific threshold that could fundamentally transform how our planet absorbs solar energy. The reality of a blue ocean event. As researchers track the downward trend lines at both ends of the globe, they are closely watching a specific milestone that used to belong purely to science fiction. That threshold is known as a blue ocean event. In simple terms, it refers to the moment when the floating ice extent in a polar basin falls below 1 million square kilometers. At that point, the remaining frozen cover would be pushed into isolated pockets along the coastline, leaving the vast majority of the polar sea as wide-open, dark blue water. If you look at satellite images today, the tops and bottoms of our maps still show up as bright white shields during seasonal peaks. But as summer melting seasons get longer and winter recoveries get weaker, computer models project that we could see a blue ocean event occur during the seasonal minimum in the coming decades. Even stranger, because both poles are breaking down simultaneously, scientists are considering the realistic possibility of seeing low ice conditions unfold at both ends of the planet within similar time frames. To be totally clear about what this concept means, a blue ocean event does not mean that every single ice cube on Earth vanishes overnight. It refers specifically to the seasonal minimum dropping below that defined 1 million square kilometer mark for a few weeks before winter freezing begins again. But even a brief period of open blue water changes the game for global climate physics. Without that bright white cover sitting on top of the sea, the polar ocean stops bouncing solar radiation back out into space and absorbs nearly all of it instead. That sudden influx of heat warms the top layer of the ocean water, making it significantly harder for winter ice to reform when the sun goes down again. That stored warmth carries over into the next season, creating a lasting thermal imprint that drags down future recovery efforts for years to come. The real-world impacts of crossing that threshold reach far beyond the polar circles. A warm and ice-free ocean alters the atmospheric pressure balance between the equator and the poles, which directly shapes global storm tracks and agricultural weather patterns across North America, Europe, and Asia. It also threatens to disrupt major ocean currents that regulate global heat distribution, while accelerating the melt rate of nearby land glaciers that directly drive up global sea levels. Hysteresis and the future of polar science. When you look at the simultaneous changes playing out across both poles, it is tempting to assume that if global temperatures ever stabilize or cool down, the ice will simply grow back on the exact same timeline it lost. But according to Hysteresis, that is actually not the case. Quite simply, hysteresis means that the path a complex natural system takes to fall apart is completely different from the path it needs to recover. Taking thermal energy out of an ocean system takes significantly longer than pumping that same energy in. Once you melt a large ice sheet and expose dark, open ocean water beneath it, you change the physical rules of the entire region. The dark water absorbs heat, warms up the upper ocean layers, and destroys the protective cold buffer that used to shield the area from below. Even if atmospheric temperatures drop back down to where they were 20 years ago, that stored ocean heat continues to resist freezing from underneath. To get the exact same thick ice cover back, the planet actually has to get significantly colder than it was before the melting ever started. This non-linear physics is precisely why climate scientists tracking current satellite data are so deeply concerned about what just happened at both ends of the world. They are not watching a temporary wobble in the seasonal cycle, but two highly complex physical systems cross internal tipping points, where the natural feedback loops begin actively driving their own decline, regardless of minor year-to-year weather fluctuations. The real-world consequences of this polar instability reach straight into the daily lives of people living thousands of miles away from the nearest ice sheet. The temperature difference between the warm equator and the cold poles is the fundamental engine that drives global atmospheric circulation. As both poles lose their ability to reflect sunlight and cool the planet, that temperature gap shrinks. That shrinking gap weakens the high-altitude jet stream, causing it to stall and lock extreme weather patterns in place. That is why we see prolonged heat waves and unseasonal winter freeze-ups lingering over agricultural belts and major metropolitan areas for weeks at a time. At the exact same time, the rapid retreat of land-based glaciers like Hector sends more fresh water pouring straight into the global ocean. That surge of land ice melt accelerates sea level rise along heavily populated coastlines, while simultaneously threatening to disrupt deep ocean overturning circulation, which is the planet's global conveyor belt that redistributes heat around the world. Understanding these underlying physical mechanisms, rather than just reacting to scary headline numbers, changes simple anxiety into genuine and actionable awareness. Scientists using continuous, all-weather microwave satellite sensors operated by NASA, NSIDC, and JAXA will keep tracking every single square kilometer in real time, analyzing whether the Arctic settles into its new baseline and whether Antarctica's triple whammy drivers continue reinforcing each other over the coming seasons. Both ends of our planet just proved that temporary stability and true permanence are two very different things, and the data proves the Earth system is changing faster than early models ever anticipated. If even the world's top scientists were completely caught off guard by these sudden and simultaneous crashes at both poles, do you think our global weather is about to become far more unpredictable than we were ever prepared for? Or is this strange breakdown at both ends of the planet just a natural cycle that the ice will eventually bounce back from? Leave your answers in the comments below. Don't forget to like the video and subscribe to the channel. Thank you for watching, and if you enjoy this video, please click on the next one on your screen.